Imagine you're out on this beautiful, scenic hiking trail. The sun is shining, the birds are singing, and, you brush up against this leafy, unassuming green plant right off the path.
Right, just a totally normal hike.
Exactly, you don't think anything of it. But then a few hours later, your arm is covered in this incredibly itchy, blistering, just downright miserable rash. You have just met poison ivy.
Ouch. Yeah, that is not a fun realization.
No, it's the worst. But now I want you to imagine taking that exact same toxic sap, the literal chemical that just caused you days of agony, and using it to paint a beautiful, shiny box.
Which sounds completely absurd. I mean, why would anyone do that?
Right. And not just any box, but a box that will survive being buried underground for 2,000 years. A box that resists acid, boiling water, and just general decay.
It's a profound contradiction, really. You are taking this fragile, highly toxic biological defense mechanism from a plant and somehow transforming it into an indestructible, permanent armor.
It's wild. Welcome to the Deep Dive Lab. Today we're answering a really strange mystery. Why does a highly toxic tree sap, closely related to poison ivy, create one of the most durable, beautiful, and long-lasting materials in human history? Yet if you leave it out in the sun, it just crumbles.
Yeah, and what's fascinating here is that this isn't simply a niche topic for, art historians. What we're looking at is a masterclass in complex polymer chemistry and bioengineering.
Humanity just kind of stumbled onto it, right?
Completely by accident,
Oh, right.
millennia ago. And modern science is only just now figuring out the molecular mechanics of how it actually works.
Okay, let's unpack this. Our mission today is to investigate the ancient, deeply contradictory science of Asian lacquer. We're going to explore how this bizarre material cures, why sunlight is its absolute worst enemy, and how modern scientists are reverse engineering its toxic properties right now.
And they're using those properties to build the eco-friendly, bacteria-killing technologies of the future. It's really incredible stuff.
So to really grasp those future applications, we have to look at the immense effort it took to utilize this material in the past, right?
Exactly. I mean, for centuries, artisans in China, Japan, Vietnam, and other parts of Asia harvested this tree sap. It's known as qi or urushi.
Right.
And they used it to coat bowls, armor, furniture, works of art, you name it.
I just want to pause here and think about the sheer human effort and the risk involved there.
Oh, the risk was massive.
Right. Ancient artisans were willingly harvesting a sap that caused severe allergic contact dermatitis. They were essentially milking poison ivy trees, suffering through unimaginable rashes, just to make a bowl.
Yeah, they must have known the end result was practically magic, or it wouldn't have been worth it.
It had to be.
And the archaeological record certainly backs that up. If you look at artifacts from the Jomon period in Japan, which, stretches back thousands of years BCE, or from ancient Chinese dynasties.
Well, they still look good.
They have been dug out of the earth looking practically brand new. Yeah, this coating can resist harsh acids, it can resist boiling water, it can even sit in seawater for centuries without degrading. It basically functions as an organic, biological plastic.
I think most people, if they think about lacquer at all today, probably assume it works like that can of semi-gloss sitting in their garage.
Right, the stuff you just brush on a chair.
Exactly. You brush it on, the water or the chemical solvents evaporate into the air, and the paint just dries. Simple.
That is the standard assumption for evaporative drying, where a liquid turns into a solid simply by losing its solvent. But Asian lacquer completely defies that logic.
Because they didn't just leave it out to dry.
No, not at all. Ancient artisans took their freshly painted lacquerware and immediately put it into dark, highly humid, sealed wooden cabinets to cure.
Wait, highly humid? That's like trying to bake a cake in a wet sauna. It makes no sense.
I know, it sounds crazy. The wet sauna analogy highlights the fundamental difference perfectly, though. Asian lacquer doesn't dry. It chemically transforms.
Oh, I see.
But before we explore the mechanics of that transformation, we have to introduce the paradox that completely baffled museum conservators for decades.
Right, the vulnerability.
Yes, we have this legendary durability, but it comes with a crippling weakness.
You take this invincible ancient armor, put it in a modern museum display case near a window, and when it's exposed to light, specifically the UV light from the sun, it just falls apart.
Yeah, conservators call this condition surface blanching. The material loses that deep, beautiful gloss. It turns cloudy.
It just fades.
Worse than fading. Suddenly, this impenetrable coating that could survive boiling acid becomes highly sensitive to ordinary water and mild solvents.
Wait, water can damage it now?
Exactly. It develops an Achilles heel that seems entirely out of character for a material this tough.
So if this material is a biological plastic that survived centuries underground, conservators couldn't just guess why the sun was killing it.
No, they had to force it to fail in a controlled environment to watch the exact chemical breakdown.
Right. But to understand how it breaks, we first need to understand how it's built. What is actually happening inside that dark, wet sauna?
Well, we can find the blueprint for that buildup in a really fascinating recent paper. It was published in the journal Polymers in 2025.
Okay, what did they find?
The researchers detailed the precise chemical cascade. The raw tree sap contains an enzyme called lacase, alongside these highly allergenic compounds called urushiol, lacquer, and phtisi.
And urushiol is the exact same chemical compound that makes poison ivy so notoriously itchy, right?
Spot on. It's a catechol lipid, which is a specific type of organic molecule that our immune systems aggressively reject.
So how does it harden into armor?
Well, in the presence of moisture and oxygen, that lacase enzyme acts as a biological catalyst. It actively links those toxic urushiol molecules together, forcing them to bond.
Like chemically bonding them?
Yes, into a tightly packed, three-dimensional structure known as a shell-core polymer network.
Ah, so the water isn't something that needs to evaporate away. Moisture is actually the mortar.
That is a great way to put it. Without water, the lacase enzyme is like a construction worker locked out of the building site.
The enzyme stays dormant, and the sap just remains a sticky, toxic mess.
Exactly. The moisture allows the lacase enzyme to initiate what's known as radical polymerization. You can think of it like setting up a massive, intricate line of dominoes.
Oh, I love a good domino analogy.
Knocking one over forces thousands of others to instantly lock arms. The moisture pushes the first domino. The sap builds a molecular fortress.
Okay, so we have this moisture-built molecular fortress. How did scientists figure out why UV light destroys it?
This brings us to a groundbreaking 2018 study. It was presented at the International Symposium on Ancient Chinese Lacquerwares in Shanghai.
Who was running it?
It was led by Dr. Jing Han and her colleagues from the Getty Conservation Institute.
And they wanted to see exactly how it breaks down.
Right, Dr. Han's team wanted to understand the degradation at a molecular level, so they created sample boards using those traditional ancient recipes.
So mixing the urushiol, lacquer, and phtisi with natural stuff like tung oil and perilla oil.
Exactly. And then they subjected these beautiful traditional boards to absolute scientific misery.
I love this part. They put them into a device called an Atlas weatherometer, which, I mean, you're essentially looking at a specialized torture chamber for ancient art.
That is basically what it is, yeah.
They blasted the samples with a water-cooled xenon arc lamp, delivering 259 kilojoules of light over 144 hours a week. And while they were blasting it with intense light, they were rapidly cycling the humidity.
Right, from a bone-dry 20% up to a soaking 95%.
I assume fluctuating the humidity like that isn't just to make the surface wet, but to force the underlying wood to constantly expand and contract, basically simulating a century of physical stress in a single week.
That's the exact methodology. They needed to induce microcracking to mirror centuries of environmental stress in a highly compressed time frame.
So they torture the wood, and then how do they measure what happens?
They deployed an impressive array of analytical technology, specifically ATR, FTIR, and PyGCMS.
Okay, alphabet soup time, which translates to attenuated total reflection Fourier transform infrared spectroscopy and pyrolysis gas chromatography mass spectrometry.
Impressive pronunciation.
Thank you. I practiced. But for those of us who don't spend our weekends in a chemistry lab, they're basically bouncing infrared light off the surface to read its molecular fingerprint, right?
Yep, and then instantly flash frying tiny samples so the pieces fly into a detector to be weighed and identified.
That is so cool. So what did they find when they flash fried the samples?
The findings were startling. The UV light doesn't just fade the pigment on a superficial level, it literally chops up that dense polymer network.
Wait, it physically chops it up?
Yes. The light carries enough pure energy to physically sever the chemical bonds that the lacase enzyme works so hard to build in that wet sauna.
Here's where it gets really interesting. When those bonds break, the physical properties of the lacquer go completely haywire.
They absolutely do.
As the polymer network gets chopped up, the surface pH of the lacquer plummets. It drops from a stable, neutral state down to a highly acidic state. We're talking a pH between 4.1 and 2.5.
And that acidity is the absolute smoking gun of the degradation process. Breaking those polymer chains creates new chemical compounds called acid catechols.
Acid catechols.
Right. When you shatter a polymer, The resulting fragmented pieces react with oxygen in the air to form acids.
Oh, wow.
And this fully explains why the blanched lacquer suddenly becomes sensitive to water. The new acidic compounds resting on the surface are water-soluble.
So rain or even just high ambient humidity in a museum can literally start to wash the ancient surface away.
Exactly. It's dissolving its own ruined armor.
But it doesn't just turn acidic, though. Under the UV light, the lacquer actually starts to glow.
Yeah, the autofluorescence. The researchers noted that this glowing spikes heavily during the early stages of UV exposure and then, eventually dies down.
Why does it glow?
If we connect this to the bigger picture of polymer chemistry, that glowing is the optical signature of the material dying.
That sounds so dramatic.
It is. As the UV light breaks the polymer chains, it creates intermediate aging products, specifically conjugated carbonyl groups.
Okay, conjugated carbonyl group.
Think of these molecular groups like broken springs in a mattress. When UV light hits them, the energy gets trapped, bounces around inside the structure, and is re-emitted as visible light. The surface physically glows.
That is wild.
But as the UV exposure continues relentlessly, even those intermediate products are destroyed, the broken springs disintegrate, and the glowing stops.
And as a final insult, the lacquer filament actually becomes transparent. The internal structure completely collapses, allowing light to just pass right through it.
Right. For museum conservators, this outlines exactly why priceless artifacts look faded and washed out.
Sunlight isn't bleaching the color. It's chemically shattering the armor, turning it into a water-soluble acid, making it glow, and then making it invisible.
It's a tragic reality for art conservation. But, observing destruction usually leads to a new beginning in material science.
Because knowing exactly how a material dies provides the precise blueprint needed to rebuild it.
Exactly.
So, what does this all mean for us today? We understand how this toxic sap cures in a humid environment, and we know how UV radiation acts as a lockpick to meticulously dismantle it. How do we take that forensic knowledge and apply it?
Well, we stop trying to merely save old museum pieces, and we start actively stealing nature's recipe. Modern chemists are reverse engineering this thousands of years old chemistry to solve 21st century problems.
Which brings us to a brand new, incredibly exciting 2026 study published in the journal Coatings.
Yes, this is the really cutting edge stuff.
This research was conducted by Kaiyao, Ji Tian, and Perong Huang. They decided to look right back at the source material. That exact toxic rash-inducing compound we talked about at the beginning, urushiol.
They recognized that the specific chemical structure making urushiol so durable as an ancient lacquer also gives it some hidden, highly desirable properties for modern applications.
Okay, but I definitely have a pushback here.
Go for it.
Are we seriously trying to paint our modern world with poison ivy sap? I mean, OSHA would have an absolute field day with that. You cannot spray down a hospital waiting room with a chemical that puts half the population into anaphylactic shock.
That is a very fair point. But bioengineering completely removes that risk.
Oh, thank goodness.
The brilliance of Yao, Tian, and Huang's research is that they didn't just use raw, unrefined urushiol. They modified the urushiol oligomer at the molecular level.
An oligomer is essentially just a short chain of molecules, right?
Exactly. And through targeted chemical synthesis, they acted like microscopic surgeons, taking molecular scissors and snipping off the specific allergenic carbon tail that triggers the human immune system.
So they snipped off the rash part?
Yep. They stripped out the toxicity entirely, but they left the tough, structural phenolic rings completely intact.
Wow. So they created what they call bio-based UV-curable polyurethane acrylate resins.
That's a mouthful, but yes.
Polyurethane acrylates are everywhere in modern manufacturing. They're the tough, glossy coatings on hardwood floors, on electronics, on cars.
Right. But historically, we've had to rely heavily on fossil fuels and petroleum to manufacture them.
So the shift from petroleum to a bio-based alternative is a massive environmental victory on its own.
Absolutely. Instead of pulling oil out of the ground, we can utilize vegetable oils and modified tree sap to create industrial-grade plastics and coatings.
But the environmental aspect is really only half the story here. The real breakthrough is what this new bio-based coating actively does.
This is my favorite part.
Because they kept the residual chemical structure of those tough phenolic rings from the urushiol, these new coatings naturally destroy bacteria.
And we aren't just talking about mild everyday germs.
No. The researchers proved that these urushiol-based coatings actively destroy drug-resistant superbugs, including Staphylococcus aureus, which is notorious for causing severe, sometimes fatal, hospital-acquired infections.
And Helicobacter pylori, which causes stomach ulcers and gastric cancer.
The translation of a toxic plant defense mechanism into a modern antibacterial surface is just brilliant.
It really is. Those specific phenolic rings in the modified urushiol structure essentially act as microscopic spears.
Microscopic spears.
Yeah, when bacteria land on the cured surface of this coating, those molecular spears physically pierce and disrupt the bacterial cell walls. It's a mechanical kill.
The bacteria literally burst open.
Exactly. And because it relies on physical destruction rather than chemical poisoning, bacteria have a tremendously difficult time mutating or developing resistance to it.
That is incredible. But I am spotting a massive contradiction here, though.
What's that?
We spent all this time talking about how UV light is the ultimate enemy of urushiol. Dr. Hahn's research at the Getty proved that UV light shatters the polymer network, drops the pH, and destroys the material.
Right, the surface blanching.
So if Yao, Tian, and Huang are making a brand new coating out of urushiol for hospitals, won't it just, melt in the sun?
This represents perhaps the most elegant part of the 2026 research. They flipped the vulnerability on its head.
Flipped it how?
In traditional Asian lacquer, UV light slowly breaks the bonds over years of exposure. But modern chemists chemically attached acrylate groups to the modified urushiol.
Acrylate groups.
Right, and acrylate groups are highly reactive to ultraviolet light.
Yeah.
By combining them, the scientists designed these new coatings to deliberately cure instantly when exposed to a specific intense flash of UV light.
Oh, wow. They weaponized the UV reactivity.
They absolutely did.
Instead of needing to sit in a dark, wet sauna for weeks so the lactase enzyme can slowly build the network, the modern manufacturing process uses a quick blast of UV light to instantly freeze the polymer into an indestructible, bacteria-killing shield.
The light forces the bonds to form rather than breaking them apart.
That is genius.
It adapts the ancient material perfectly for high-speed modern manufacturing. Picture a conveyor belt producing medical devices, or sterile hospital tray tables, or high-touch grab handles for public transit.
Things that constantly get covered in germs.
Exactly. These items get coated in the liquid, eco-friendly, urushiol-based resin. They pass under an intense industrial UV lamp for a fraction of a second, and they emerge completely solid, instantly sterile, and perpetually hostile to superbugs.
We took a process that used to demand ancient artisans spend months performing careful, highly toxic, high-humidity labor, and we can now execute a better, safer version of it in less than a second using the exact type of light that used to destroy it.
It perfectly illustrates how a deep understanding of degradation chemistry gives material scientists the exact blueprint they need.
Right.
Knowing exactly how and why a material fails down to the dropping pH, the acid catechol, and the autofluorescence allows us to build a better, stronger, and more purposeful version of it.
We have covered a massive amount of ground today, from ancient hiking trails to modern hospital wards. Let's zoom out and pull this all together.
Sounds good. We started by analyzing traditional Asian lacquer, seeing how it relies on an incredibly delicate, counterintuitive dance.
The wet sauna.
Right. It requires enzymes, toxins, and high moisture acting as mortar to cure into that legendary shell core polymer network.
Then, thanks to the forensic work at the Getty Conservation Institute, we saw exactly how UV radiation acts as a lockpick, meticulously dismantling that chemical armor.
By breaking the polymer chains and causing the material to visually glow as it dies.
Finally, we saw how researchers in 2026 took all of that ancient wisdom and modern forensic chemistry, and they snipped the toxic side effects away from the urushiol.
They utilized its hidden mechanical strength to create the next generation of eco-friendly, bacteria-killing materials that cure instantly under UV light.
It is a remarkable journey of chemical discovery, bridging thousands of years of human ingenuity.
It really is.
The big picture insight here is that human understanding of science is rarely a straight line. Sometimes it involves taking a folk art that is thousands of years old, recognizing the hidden genius in its molecular structure, and bringing it into the 21st century to solve incredibly modern problems.
Problems like antibiotic-resistant superbugs and our heavy reliance on petroleum plastics.
Exactly. We didn't have to invent a completely new chemical from scratch. We just had to listen to what the ancient trees were already doing and then refine the process.
Nature has had millions of years of research and development. We're just finally learning how to read the patterns and adapt them safely.
That leaves us with a pretty provocative thought to ponder. If we can reverse engineer a 2,000-year-old toxic tree sap something that causes horrific rashes into a cutting-edge, life-saving medical coating, what other ancient, seemingly dangerous natural materials are just waiting in the forest for a chemical makeover?
What other wild poisons are actually the life-saving cures of the future? Just waiting for the right scientists to crack the code.
There is always more to learn from the natural world.
There always is.
Thank you so much for joining us here on the Deep Dive Lab today. If you enjoy taking this journey with us, we warmly invite you to follow and subscribe for more fascinating science stories uncovering the mysteries of our world. We'll see you next time.